Hi kids, we're back and we want to talk about section 4.5. You may have noticed we jumped over that and went to 4.6 the other day when we talked about power. We're going to spend quite a few days on 4.5. There's a lot here. I want to take our time to really discuss it, go through some examples. So we're going to be really patient on this topic. It's called thermal energy and heat. You may have heard the word heat before. Now it has a very technical definition. You might have heard the word thermal energy, maybe not, maybe just the word thermal associated with things heating up or cooling down, like a thermos or a thermal blanket, things like that. Probably heard of the word temperature, and some people would have confused temperature with heat if they didn't really understand it, where it has a technical, very specific definition. So uh, we want to go through these and understand them. So what we've done here is defined all of these terms for you, all listed out here. You can do it on your own or copy this out, whatever you like. And we're also going to talk about how things allow heat, thermal energy, I should say, to move from one place to another, one of them being conduction. All right. You heat the bottom of a fry pan, but after a while, the whole fry pan is hot, not just the bottom where the heat source comes from. Uh, why is that? We need to understand that. We're going to talk about things like convection. Why is it that we have uh, the registers, the little vents, the holes that bring heat into our home from our furnace? Why is that usually on the floor and not on the ground? What's going on there? How does convection help us understand how that can move energy around and help heat our homes? How does that work? So we're going to talk about that. And radiation. Why is it that when we're outside on a sunny day and I have a black t-shirt on, I really feel the heat of the sun. But if I have a white t-shirt on, I don't feel the heat of the sun. Radiation, we got to understand that. So all I've done here is listed out the definitions for you. That's all that we have here. All right, I've just listed the definitions for you, and I will uh, put the link to this document on our website. So if you don't have it copied out as I'm scrolling back and forth like a crazy person, don't worry about it. I will put the document up on the website. So I'm going to divide our study of thermal energy and heat into two parts. The first part will be qualitative. That's it. No numbers, no equations. We're going to save that for the second part. So if you take a look at what I'm going to shortly post for the April 15th announcement, I'm telling everyone, look, this is day one. There's 2 days of work in here. Pace yourself. There's videos to watch, textbooks reading, questions to answer. So I'm expecting this to take 2 days. All right, you're going to read section 4.5, but only up to page 150. All right, that's your homework, and then do these questions. If you have some misunderstanding, please let me know. All right. Um, I've posted a whole bunch of videos. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 videos to watch. They're about 5 minutes long. So that's why I'm telling you, we're going to divide this into 2 days. They're the little 4 or 5 minute cartoon videos that you've seen before. They're kind of fun. I really like them. I think they do a really good job explaining all this. All right. And then when you do your homework and you want to check your work, it's right there. You can check your work right there. But if you still have questions, I've done the homework, sir. I still have questions. Look, we've got our discussion thread. You can just click on that and start asking questions. All right. So there is a lot of work, 2 days. Pace yourself, please. So one of the phenomenon that we want to explore is how thermal energy is transferred through heat from something that's warmer. Look, this beaker, beaker A, it's an insulated beaker. It's not a special kind of beaker, okay? It's at 95 degrees Celsius. This beaker is at 5 degrees Celsius. They're also an insulated beaker, all right? And we want to understand how we can get thermal energy from here, the hot, into the cold, because the transfer of thermal energy, heat, always goes from the warmer to the cooler. And as you watch some of the videos that I've asked you to watch, you'll understand that. But let's take a look at what's going to happen here. So look, the temperature changes here, all right? And it goes to about being the same temperature, happen rather quickly here. I'm going to pause it now. And if we take a look here, it happened at about 1,000 seconds. About 1,000 seconds. If you take a look here, the temperature in beaker A was coming down, and the temperature in beaker B was coming down, and around, give or take 1,000 seconds, around there, they both hit 50 degrees, and they stay at 50 degrees. That's it. All right? Why is that happening? That's what we want to be able to understand as we go through here. Now let's change the type of uh, substance that is connecting these two beakers. Now it's this aluminum, piece of aluminum that's been curved and put into each one. What about if we try copper? What's going to happen here? Same thing. Starts at 95 degrees Celsius in beaker A. Beaker B is 5 degrees Celsius. What's going to happen? Oh, very interesting here. Beaker B lost temperature. A lost temperature. Beaker B gained temperature. All right. And they both settled at 50 degrees again. But look, they kind of came together. I don't know. What is that? 500, maybe a little bit more. But it took a lot less time. We're talking in the 500 second ballpark. It took a lot less time for both beakers to reach the same temperature of 50 degrees Celsius, a lot faster than when we are using aluminum. Why is that? Why is that? That's one of the things we want to be able to understand as we go through this section of the textbook. Let's do one more, something totally different, not even a metal, glass. All right, so we're going to start at 95 degrees Celsius again. This one's at 5 degrees. Everything's the same, except we change the connection to a piece of glass that's been bent. Well, let's start. Let's see what happens. Oh, Nelly. Look at these graphs. You can see a little bit of temperature change. Look at that. A little bit of temperature change. But it's slow. They're barely approaching each other, and we're up to 2,000 seconds. This only went from 5 degrees up to 7 now. I'm not going to waste our time and let this run forever, but I think we can all agree this would take a long time for there to be a same temperature in both. They've reached 50 degrees again, but it would take a long time. Why is that? Well, that's why we're studying this section of the textbook. Well, here's another nifty gizmo, and just like the last one that we saw, I'm going to use it to kind of pique our interest, to get our curiosity going, to motivate us to study this section of the textbook here. So you've got a thermometer hooked up here. Okay, it's reading 20 degrees Celsius, and white light is shining onto this. All right, and I'm going to put a piece of metal there. It looks, some of the light is being reflected. Okay, and we're going to let this run and see what happens to the temperature registered on the thermometer. Okay, it's going up, and after 3 hours, it got to 21.7 degrees Celsius. So somehow there was some heating going on because the white light was shining onto it. Why is that? That's why we're studying this section of the textbook. Let's put a glass dome over it and repeat what happens. Let's see. Oh, temperature's picking up. Aha, there's a difference here. The glass dome had an effect in the final temperature after 3 hours of heating from the white light. Why is that? Hmm, very interesting. What about if we put a black brick here and start the same process? Let's take the glass away. Just the black brick. It starts at 20 degrees Celsius again. Much difference in the amount of temperature. Look, 34.3 degrees Celsius after 3 hours of being exposed to the white light. Interesting. Let's put a glass cover over it. See what happens. Hmm. After 3 hours of heating, almost 47 degrees Celsius. Interesting. Why? Why is this happening? And the last one we're going to try is water. Still some reflection going on here. Okay, let's heat her up. See what happens. 28 degrees Celsius. Interesting. Let's put the glass cover on now and heat her up. 31.7 degrees Celsius. Remember, we're studying this section of the textbook because by the end of the studies, we want to be able to explain this and understand this, okay? All right, here's another nifty gizmo. And it's taking a look at what happens to the speed of particles, their velocity, as the temperature changes. So we've got hydrogen here, and hydrogen is H2. You know that from your chemistry. And we're at about 50 Kelvin, very low temperature. And when we're at 50 Kelvin, we're saying that this grouping of hydrogen, the most probable velocity would be 642 meters per second. The mean velocity, a mean is an averaging, is about 725 meters per second. Okay, so let's heat this up to, oh, I don't know, 120. See how the graph changes? Here's velocity and the probability of finding a particle at that particular velocity. See, they're not all at the same velocity, but there's a pattern to how the velocity of the particles are distributed. So here's the most probable velocity now, 995 meters per second. Here's the mean velocity and averaging over just over 1,000. All right. So I'm showing you this once again to get you interested into studying this section of why do the particles change in their motion as the temperature changes. Look, it's up to 600 Kelvin. So that's quite a bit of heat there now, quite a bit of temperature. And look at the hydrogen's motion. Why is that? Well, we need to study this section of the textbook to understand that. Look at the most probable velocity now. Look, it's skyrocketed as we're using this gizmo to understand this. Look at the averaging, all right, also skyrocketed. So just use these gizmos to hopefully pique your interest in studying this unit, and take your time through this. If you have any questions, let me know, and I hope everyone has a great day. Bye-bye.